Hey guys, this is Professor Janacek, and I want to talk about derivatives. Now this is one of the big topics in calculus. Very exciting. Let's start with an idea that we already know. Let's talk about slope. I want to specifically look at slope of a secant line. If you're not certain what a secant line is, I have several drawn over here in green. A secant line basically goes through 2 points on a curve. So I've got a point here and a point there, and each of these green lines, it crosses that curve at 2 points. That's a secant line. To find the slope of a secant line is just like to find the slope of a line. We often call that m, if you remember. This is f of x minus f of a over x minus a. You could also think of this y2 minus y1 over x2 minus x1, where my y2 is f of x, and my y1 is f of a, and my x2 is just x, and my x1 is just a. So it should look somewhat familiar. Now to find the slope of the tangent line, first off, what is a tangent line? Oops. Well, that is this blue line here. Notice it's only intersecting my curve at 1 point. Well, how in the world do we find a slope with just 1 point? I mean, I know how to find slope with 2 points, but with 1 point, what in the world are we going to do with that? Well, we are going to use a limit. So what we're going to do is we're going to take the limit as my x values are getting closer and closer to that a, and we end up with the limit of this slope function. So you'll notice that the idea is that here this is a, and my x values, I'm on the x-axis here, so my x values are getting closer and closer to a from either direction. Now there are a couple of concepts that we like to think of with the slope of the secant line, or slope of the tangent line. Slope of the secant line, you could say, is like the average rate of change. That's very common concept. And a very specific rate of change that we like to look at is velocity. So that would be like the average velocity. So that the slope of the tangent line has similar concepts behind it, but this one, instead of average rate of change, the tangent line is at a specific point, a single point, so it's an instantaneous rate of change. Or the instantaneous velocity. Which is really pretty amazing. Again, finding the slope or rate of change or velocity, if I have 2 points, that's not so bad. But now we're doing it at just 1 point, a single point. We can find what the velocity is. Again, pretty awesome idea. Now let's get into the derivative. First off, here's how we'll write it. F with this little hash mark at the top of x. So we're using function notation, so we are working with the idea of a function. And we define it to be, you'll never guess, this is the limit as x approaches a of f of x minus f of a over x minus a. So yes, the derivative can be interpreted as the slope of the tangent line or an instantaneous rate of change. There is another way of writing this. We'll use the limit as x approaches a of f of x plus h minus f of x all over h. This is referred to as the difference quotient, the limit of the difference quotient. Actually, I'm sorry. That should be as h approaches 0. Just rewriting the other one. So the limit as h approaches 0 of our difference quotient. Again, this guy here is referred to as the difference quotient. The way we say this is f prime of x. That's how that's read. I want to kind of informally go over how these two things are the same. Now again, the idea, this one hopefully you can see, all right, I just take my slope of a secant line, take its limit as my x value gets close to the a value, and we're good. But now how do I go from that limit to this thing with the h's? So again, just kind of informally, we'll let x be a plus h. So the idea with this one, notice x is approaching a. So suppose x is approaching 5. Well, then that means I could say x is equal to maybe 5 plus 1, which is just a little bit, or 5 plus 1/10, or 5 plus 1/100th. Not too far. Of course, we could continue on with that. But the idea is that my x value, x, is equal to my a plus a little. So it's getting really close. I could also go the other direction and have that h value be a negative. Same idea, but so that's why I'm letting x equal to h. I'm sorry, x is equal to a plus a little bit. So think of h as a little bit. All right, if that's the case, then we also know that h is equal to x minus a. So as x approaches a, then we know that x minus a approaches 0. Okay, see that? And x minus a, we've just determined that is h. So h approaches 0. So that's how we'll go from the limit as x approaches a to the limit as x approaches 0. All right, using this same little substitution that x is equal to a plus h, let's see if we can take this f of x minus f of a over x minus a. And so I'm going to try to take this bit and see if we can come up with that bit. Well, let's see here. We have f of, instead of x, I'm going to use a plus h minus f of a. All right, that's looking pretty good. Over, in the denominator, we have a plus h minus a. All right, so the denominator, we could see, I'm going to leave the numerator as is, but in the denominator we can see that, oh, the a's become 0. Combine those, we get 0. We just have h in the denominator. Fantastic. Now all I need to do is, this is very close to what I want. Almost there. It's just that instead of a's, I want x's. However, we know that as our x is getting close to a, we know at some point the idea is that x is going to get very, very close, that they're practically indistinguishable. And so if I simply replace the a's with x's, then you can see there it is. We have this bit right there. All right, so that's the idea there. All right, so a couple things. Let's see. F prime. We say f prime is the derivative of f. So you'll sometimes hear me say f prime of x, and sometimes you'll simply hear me say the derivative of f. They mean the same thing. I want to talk a little bit about notation. We do have this notation, f prime of x. Again, that reminds me that it's a function, but remember, functions f of x, we often used y to represent them, so I could do the same thing here and use y prime. We also have this df dx. That's telling me I'm taking the derivative of f with respect to x. We could also write that as dy dx. Sometimes when that function is too much to write in the numerator of that little notation, I'll write d dx of f of x. This allows me to kind of set it off to the side and write it much longer. And in some cases you simply see an uppercase d followed by the function f of x. Now, if we're looking at a specific a value, I want to find the derivative at a specific a value. There are certain ways of denoting that. I can simply say f prime of a, so that means, again, evaluate the x at a. We could also use the y prime notation, but what we'll do is we'll write this little vertical line and then say, okay, I'm going to evaluate it at x equal to a. Same thing works for the f of x, df dx notation. Again, I could put this vertical line and say, okay, I'm going to evaluate this at x equal to a. Or dy dx, you could use that same notation, evaluate it at x equal to a. Or you could use this uppercase D followed by f of a. I will most likely be using the first few notations, like I use this one, we use that one, very common, and this one, of course. Actually, here you can use almost any of those, but with the evaluation, almost always we'll see the first one used. All right, couple other things. If f prime exists, so I can find the derivative, I can actually take the derivative, then I know that we can say that f is differentiable. If f is differentiable, then we know that f is continuous. Oh, we talked about continuity previously. Now, I can also say if f is differentiable, then f is continuous. I can also say that if f is not continuous, then f is not differentiable. Ooh, let's see. Now, what is that about? Let's first remind ourselves what not continuous means. When is a function not continuous? Well, when it does not meet the three conditions for continuity. That, just as a reminder, that means that f of a does not exist. Right? For continuity, I needed f of a to exist, and so if it's not continuous, that means this does not exist. Also, the limit, for continuity, the limit at a, as x approached a, had to exist, but if I'm looking at not having continuity, then the limit as x approaches a, again, does not exist. And then finally, the third condition for continuity was that the limit was equal to the function value, but so in this case we're looking at not continuous, so the limit as x approaches a of f of x is not the function value. So these are the three things that would tell us that it's not continuous. Again, this is kind of the opposite of each of those conditions for continuity. I also want to take a moment and point out, so here I have f is differentiable followed by then it's continuous. So again, if it's differentiable, then it's continuous. And then I follow that by the statement, if it is not continuous, then it is not differentiable. So notice I've done a couple things. I've added nots here, and then we've also turned these around. Continuous, continuous, those get swapped. Differentiable, differentiable, they get turned around. How can I put all of this together to make it make sense? Well, that's actually a little game in logic. So let's take a logic interlude, or perhaps it's a logical interlude. If you've never studied any logic, it's quite fun. So we'll start with a statement, just a basic if-then statement. If P, then Q. All right, there's our if-then statement. Whatever P and Q is. All right, if P, then Q. Now, we have what's called the inverse of that statement, which says if not P, then not Q. That's referred to as the inverse if I put nots in front of both P and Q. We also have something called the converse. Converse of a statement is when I just turn it around. If Q, then P. So the inverse, I put nots in front of each part of the statement. The converse, I turn the statement around. What if I want to put knots in front of it and turn it around? That is called the contrapositive. So that would be if not Q, then not P. That's called the contrapositive. So it turns out that if my statement is true, so if this is true, then the inverse, well, I don't know. It might be true, but it might not be. So I'll say it's not necessarily true. That's also the case for the converse. It might be true, it might not be, I'm not sure. So it's not necessarily true. However, this is fantastic. The contrapositive is true. If I have an if-then statement that is true, I know that the contrapositive is also true. Isn't that awesome? That allows me to go from the statement if f is differentiable, then it's continuous, followed by the statement if f is not continuous, then it is not differentiable. Ah, that's awesome. So again, don't forget what it means to be not continuous. If I have those conditions, I know it's not continuous, but then I also know it's not differentiable, which means I can't take the derivative, which means I can't find f prime. Right, well, there you go. Enjoy.